Dear students, welcome to the third lecture on Lyapunov stability theory. In the previous two lectures, we have seen the sufficient condition for the stability of the nonlinear dynamical system dx by dt equal to f of x, f of 0 equal to 0. The stability at the critical point was analyzed. So, in those two theorems it was given that if the Lyapunov function v is positive definite and v dot is negative definite, then the system is asymptotically stable at x equal to 0. Similarly, if v and v dot both of them are of the same nature, positive definite or negative definite, then the system is unstable, and other theorems have been seen. The theorem which is given below, it states a converse of the theorems which we discussed earlier. So, here if the system is asymptotically stable at x equal to 0 and if the function f is sufficiently smooth, fx is continuous and the partial derivatives are continuous around the origin, in a neighborhood of the origin, then there exists a Lyapunov function v. So, this is the statement of the theorem, but this theorem is of theoretical importance. We cannot it does not propose any procedure for computing the Lyapunov function as it is. So, in this lecture we will see two procedures for computing the Lyapunov functions. So, for computing Lyapunov function, we require the derivative with respect to t, which is defined like this: v dot equal to del v by del x1 into x1 dot plus etc., and x1 dot, x2 dot etc. are the dynamical system equation. So, x1 dot is replaced by f1, x2 dot is replaced by f2 etc. So, ultimately we get dv by dt equal to del v dot f in the vector notation, which is where del v is the gradient of the function v. So, now our aim is to find a Lyapunov function v. So, for this we just assume the following. Let us assume that del v is in this particular form, because del v is a vector. We say the first component is a11 x1 plus a12 x2 etc., and the nth component is an1 x1 plus an2 x2 etc., where a1 aij are also functions of xi. Okay, they are not constants here, we can assume them to be functions of xi, I equal to 1, 2, 3 up to n. Now, this aij must be chosen in such a way that the vector given here is a gradient vector and v dot should be negative definite. These two conditions should be satisfied. Accordingly, we should select the aij functions. So, if del v is the gradient vector of a scalar function, then it should satisfy this condition. It is a familiar result, because del cross del v should be equal to 0 and the component of the cross product is should be 0 here. So, it satisfies the condition del g I by del x j should be equal to del g j by del x I and I not equal to j. So, with this condition and the requirement that v dot should be negative definite, we should select the constant the functions aij. So, that is the procedure. So, to find the function v, we can follow this particular procedure. If you, because g1 dx1 plus g2 dx2 etc., it is nothing but dv by dt, and if you integrate dv by dt with respect to t, we get the function v itself. So, we can just integrate the function which is given inside the bracket and we get the function v of x. So, a procedure is given in the equation 3, we can follow this procedure and get this one. So, to see an example of this procedure, let us consider the following. So, we consider the equation x1 dot equal to minus x2 minus x1 cube and x2 dot equal to minus 2x1 plus x1 cube. So, here there is a linearization method in the study of stability theory. If the right hand side is non-linear, we linearize it and then analyze the stability of the non-linear system. If the linear system is asymptotically stable, then under some condition the non-linear system is also asymptotically stable. Similarly, if the linear system is unstable, the non-linear system is also unstable. But if the linear system is simply stable, we cannot say anything about the non-linear system. So, that was the theorem in the previous lectures by Professor Pandey, it was done. But here now if you linearize this system, what we will get is the non-linear terms will go away. So, the linear equation linearized system is simply x1 dot equal to minus x2, x2 dot equal to minus 2x2. So, if we convert it into the matrix form, we will get 0 minus 1 and 0 minus 2, and we can easily see that the eigenvalues of the matrix are 0 and minus 2. One of the eigenvalues 0 here. So, this implies the linear system is only stable. So, if the linear system is stable, we cannot guarantee anything about the non-linear system. It may be asymptotically stable or it may be unstable also. So, we cannot come to any conclusion about the non-linear system using this linear system. So, we can use this particular procedure which we have tried just now. So, we want to find a Lyapunov function. To find a Lyapunov function, V of x1 x2. So, for this we assume that the gradient of this function is a11 x1 plus a12 x2, a21 x1 plus a22 x2, where a I j are functions of x1 and x2. Now, this has to be the gradient of a function. So, now if you calculate v dot, that is dv by dt equal to del v dot f, where f is the right hand side of the differential system. So, that is nothing but a11 x1 plus a12 x2, that is the first component multiplied by the first component of the equation minus x2 minus x1 cube, then plus the second component is a21 x1 plus a22 x2, and this f2 is minus 2x2 sorry 2x2 plus x1 cube. Okay. So, that is v dot. We want that v dot should be negative definite, as well as del v should be a gradient function. Okay. Arbitrary a I j will not work here. So, we have to select it suitably. If you collect the coefficient of these things, let us say x1 square, we take the coefficient, it is equal to a11 x1 square plus a21 x1 square again, and then we take x2 square minus x2 square and its coefficient, you will get 2 A22 plus A12, and let us take the remaining x1 x2 coefficient will be minus A11 minus 2 A12 plus A22 x1 square minus A12 x1 square. So, if we take after expanding all this, we collect the coefficient in this particular way, because we want V dot to be negative definite. The bracket, the first bracket should be a positive value, second bracket should be a positive, and if we make the third bracket to be 0, then it will become a negative definite function. So, one choice is we can write A12 equal to 0 and A21 equal to 0. So that the first equation will this become A11 x1 square. So, we should take A11 to be a positive number. Similarly, A22 should be positive, so that the first two terms becomes a negative definite function. Now, we want to make this bracket to be 0. So, for that we should select minus A11, A12 and A21, both of them are 0. So, the remaining is A22 x1 square should be equal to 0. So, this implies we get A11 is nothing but A22 x1 square. So, if we arbitrarily select A22 some number 1, then we will get A11 from this equation, it is x1 square. Now, we substitute all these values in the V dot equation. So, V dot equal to minus x1 square and A11 is x1 square again. So, it is minus x2 square and A22 is simply 1, it is 2 here, and x1 x2 bracket is 0. So, only this number, it is strictly less than 0, negative definite function, we got the value V dot. Now, from here if you calculate V, that is that will be the gradient del V by del x1, that is the first value, it is A11 x1, A11 is x1 square multiplied by x1, that is x1 cube, A12 is 0. So, del V by del x1 is nothing but x1 cube, and del V by del x2, here A21 is 0, A22 is 1. So, it is simply x2. Now, if you integrate with respect to x1 the first value, so this implies V of x1 x2. If you integrate the first one, we will get x1 to the power 4 by 4, and integrate the second with respect to x2, it is x2 square by 2. So, we can conclude from this we will get del V by del x1 is x1 cube and del V by del x2 is x2 only. So, this implies V is positive definite, V dot is negative definite. So, this given system is asymptotically stable using this particular procedure. So, this is not the only way, there are infinitely many ways of finding this Aij in this particular manner. If you are not able to find any such Aij, it does not mean anything about the stability of the system. There may be some other procedure through which we can find this thing. So, immediately we cannot conclude just because this method is not working, the system is not stable, or any conclusion cannot be drawn. Okay, now we will see the second method, the Zubow's method. So, in this method it is also straightforward. First thing is we want that V dot should be negative definite and V is positive definite. So, that is for asymptotically stability. And similarly, if V dot is negative definite, V also becomes negative definite, then the system is unstable. So, we will try to find some function V satisfying any of these conditions. So, this equation is nothing but V dot del V by del x1 into x1 dot, that is equal to f1 etc. is given. We assume that V dot is equal to phi, any function which we can select it to be less than 0, that is a negative definite. We just select any negative definite function of x1 xi and put it in the right hand side. So, dV by dt equal to phi is the equation which we have. It is a partial differential equation and we can solve it using the Lagrange method in the partial differential equation and get the function V. And if V turns out to be positive, after solving this equation, if V turns out to be positive definite, then we can immediately conclude that the system is asymptotically stable. So, that is the procedure here. See, if the system is asymptotically stable, then we know that x of t tend to 0 as t tends to infinity. So, from the last step, that is dV by dt equal to phi, we can integrate it from 0 to some capital T. We will get V of x of capital T minus V of x of 0, the initial condition, equal to the integral T0 to T phi of t. And as t tends to infinity, x of t will tend to 0, and we want that V of 0 should be equal to 0. So, we can write that as t tends to infinity, this becomes 0 to infinity phi of x of t dt, and this becomes minus V of x 0, and this becomes 0 because V of 0 should be 0. So, we get this particular expression, and from here we can get the value of it is a positive because minus phi, because phi is negative definite. So, minus phi is positive definite and this expression is a positive definite function. From here we can obtain the this thing. Okay. So, we can make use of this particular procedure to find a Lyapunov function in the following way. So, let us try to find the following equation. For example, if you consider the equation V dot the simple equation x dot equal to say x cube minus x. So, to analyze, this is a one variable function. So, obviously it can be easily analyzed and this can be checked to be asymptotically stable at x equal to 0. But using this particular procedure, we will write the equation dV by dt by making use of this particular V dot is equal to phi. So, let us assume any negative function, let us say minus 2 x square. It is an arbitrary choice, it is always less than 0 except at x equal to 0. Now, if you solve this equation, this can be written as dV by dx and dx by dt, that is equal to x cube minus x, that is equal to minus 2 x square. So, this implies that dV by dx is equal to minus 2x by x square minus 1, or it is 2x by 1 minus x square. So, if we integrate both sides with respect to x, we will get this to be minus log of 1 minus x square, and in the interval mod x less than 1, this is valid. The Lyapunov function, it is always positive value because log of the number less than 1 is negative and there is a negative sign, it is always a positive value, and V dot is negative definite, which we have already selected. So, this implies that we are able to get a V and V dot as we wish in the theorem for asymptotically stable condition. So, this implies that the system is asymptotically stable. So, this is our second method, and if we have more than one variable, we will get a partial differential equation like this, and it has to be solved using the Lagrange method. Now, so far we have seen the Lyapunov theory for time invariant system, that is autonomous system. Now, for the non-autonomous system, we consider the system x dot equal to f of t comma x, where t appears explicitly in the dynamical system, and f is such that f of t comma 0 equal to 0 for all t. So, in this case, this implies that x equal to 0 is the equilibrium point. F should satisfy the condition f of t 0 equal to 0, as well as f of t x is non-zero in a neighborhood of the origin. So, then x equal to 0 is the isolated equilibrium point, and its stability can be analyzed by Lyapunov theory. So, for the time varying system, the Lyapunov function also should be a time dependent function. So, that has to be defined like this. So, for doing that, first we define what is the meaning of positive definite function for a function depending on t also. V t x is defined on the interval t0 some initial condition to infinity cross the b rho, the neighborhood of the origin. So, for example, in two variable, let us say x means x1 x2 in R2, the value of the function v of t comma x, x1 x2. So, in that case, for each t, if you fix one particular t, then we will get the surface like something like this. If v is positive definite function, it will be 0 at the point 0 0, and for any x1 x2, the value of the function v is a positive value. So, we will get a surface. Now, if you change the value of t, then we will get another surface. So, in the case of time invariant system, we got v as a single surface, but here the surface is keep on changing as t changes. So, it is not only one surface, a continuous change of surfaces we will get. Now, if it is positive definite function, then there will be a function of class k. We have seen function of class k in the previous lecture. So, we will find, so a function of class k, if we plot the graph of this in two variable, phi of norm of x. So, this is the value of the function. That means, if norm of x is constant, if you take a circle of radius r, if norm of x equal to r, then the phi value for all this value will be the same. So, it means it will be a symmetric type of surface. So, the function of class k, if you draw the surface, we will get in this particular form, where the level curves are simply circles always. Here, if you take level curves, they may not be circle, it may be ellipse or any kind of closed curve available for the function for the surface v, but here it will be always a circle. So, if v is a positive definite function, then we will be able to find a surface of class k, a function of class k like this, and which will be lying below that one. Okay. Always for any x1 x2, v t x1 x2 will be greater than or equal to this phi of this x1 x2 at the same point. So, we will be able to find a surface of class K in this particular way, then only it is called a positive definite function. So, let us see some example of this thing. So, if you take v t x1 x2, it is equal to 1 plus sine square t x1 square plus let us say 3 x2 square. So, it is always positive, both the terms are positive. So, and it is 0 only at x1 x2 are 0. Okay, so it represents a positive definite function, because we will be able to find a surface like this, it is greater than or equal to, the first term is always greater than or equal to 1 and the second coefficient is also greater than or equal to 1. We can say that it is greater than or equal to x1 square plus x2 square, this particular expression. So, this implies v t x is positive definite function. Similarly, we can find let us say v t x1 x2. If we take this to be, in the second example we take v of t x1 x2 is 1 by 1 plus t square x1 square plus say 1 plus e to the power minus t x2 square. So, if you observe here, it is also positive, always for any value of t and any value of x1 x2, both of them are positive terms and it is 0 at x1 x2 equal to 0. But here we cannot find any surface, there exists no surface, so that it is greater than or equal to some phi of x1 square plus x2 square, is not it? It is not greater than or equal to phi of x1 square plus x2 square. This type of expression we will not be able to get, because whatever surface we take, as t tends to infinity, this will become smaller and smaller, the first term becomes smaller and smaller. So, it cannot be greater than or equal to any particular quantity, fixed quantity. So, this implies it is not positive definite function. Even though the expression shows that it is always positive, it is not a positive definite function. So, now we define the next one, the decreasant function. A function is called a decreasant if v t comma 0 is 0. So, at the origin the value is 0 for all t, that is similar to the positive definite thing, but it should satisfy the condition like this. So, here we have seen that there should be a surface of class K below the surface defined by V. Now, for decreasant we should find a surface of class K above the surface V. So, that is the difference between the positive definite and decreasant. So, decreasant means if you have two variable x1 x2 and this is V of t x1 x2. So, if you have a surface V something like this, then it is keep on changing with respect to t. For one particular t this is the surface, for some other t it will be some other surface, you may get a band of surfaces. Okay. So, for different t you may get different surfaces, but all the surface from 0 to infinity should be within a band and you should be able to get another surface of class K. This is that means the level surfaces should be circle type of thing. So, that should lie above the all the surfaces V t comma x. So, V t comma x should be less than or equal to xi of norm of x, where xi denotes a function of class k. So, it should be like this. In that case, you can say that the function is a decreasant function. So, for example, let us take this example V t x1 x2. So, first we have seen that it is 1 plus sin square t into x1 square plus 3 x2 square. As we have seen, it is a positive definite function. Now, it is also decreasant because it is less than or equal to, first we have written that it is greater than or equal to x1 square plus x2 square. Now, it is always less than or equal to, we can say 3 times x1 square plus x2 square, because 1 plus sin square t is always less than or equal to 2. So, definitely less than or equal to 3, and this is also 3 here. So, it is the surface xi of x1 square plus x2 square. So, this is what we got. So, this implies decreasant. Now, if you consider this surface, if it is equal to, let us say 3 plus t square so both of them are positive expressions, always they are all positive. So, this is positive definite because you can write it as greater than or equal to x1 square plus x2 square, because here cos t can be 0 and it can be minus 1 etc. So, this will be always greater than 1, this expression greater than or equal to 2, okay, and this is always greater than or equal to 3 for t greater than 0. So, this and this both of them are greater than or equal to x1 square plus x2 square. This is the function phi. So, this implies positive definite, okay. But we cannot find any surface such that it is less than or equal to xi of x1 square plus x2 square. It is not possible, because as t tends to infinity, this coefficient keep on growing towards infinity. So, it cannot be bounded by any such function of class k, okay. So, it is not decreasant. So, now the theorem on the stability of the time varying system is like this. If you are able to find a positive definite function v and v dot is negative semi definite, then the system is stable. So, the theorem and proof both of them are exactly similar to that of the time invariant case. All the steps which we have seen in the previous lecture will hold good for this theorem. Similarly, if the function v t comma x is positive definite as well as decreasant, okay, these two conditions are to be satisfied, and if v dot is negative definite, then the system is asymptotically stable. Here we are saying that positive definite as well as decreasant, because the same condition is true in the case of time invariant also. Earlier we have seen that v of x is positive definite, that is what we have seen for, and v dot is negative definite, then it is asymptotically stable. But for the time invariant case, if a function v of x is positive definite, automatically it is decreasant also, because you can see that if a surface, because it is a single surface, we can find a surface below that as well as above that, both can be easily found out. Therefore, it is positive definite as well as decreasant in the time invariant case. But in the time variant case, we have seen example, it may be positive definite, but it may not be decreasant. So, we need this two condition to be specified for the asymptotically stable of the system, and the proof of the same the without t also holds good here. All the steps which we have shown in the previous lecture can be applied to this also, because in the time invariant case, as we have seen, it is automatically decreasant. So, that wherever the decreasant step is used, for that purpose we have to mention here separately that the system is decreasant. Okay. So, we will see here, for example, if we take x1 dot equal to x2 and x2 dot is minus alpha of t and x1 here. So, if you take this system, it is a time varying system, because the coefficient is a function of time, and 0 0 is the critical point or the equilibrium point of the system. So, in this case, define the Lyapunov function as this one, alpha of t into x1 square plus x2 square. So, if you define this Lyapunov function, it is given that alpha of t is positive definite, okay, greater than 0, and d alpha by dt is less than 0. So, under these two conditions, because this type of system occur in practical situation under this coefficient alpha to be, because if you take this, it is nothing but the harmonic oscillator in the physical situation. If you write it as a second order differential equation, this equation is nothing but the harmonic oscillator. So, it is a practical problem in which this alpha should satisfy these conditions. Okay. So, now we can take the Lyapunov function v to be like this. So, it is positive definite function, and because alpha is greater than 0, there should be a value greater than some constant k, positive constant k, because it is strictly greater than 0, and therefore, we can find the function, it is greater than or equal to this one. So, if you take the minimum of k and 1, let us call it as some other number k1, then it is greater than or equal to k1 times x1 square plus x2 square. So, we are able to find a surface like this. So, it is positive definite function, and we can easily prove that v dot is negative definite. Del v by del x1, that is alpha into 2 x1 into x1 dot is x2 plus alpha dot d alpha by dt into x1 square plus 2 x2 into x2 dot is minus alpha into x1. So, we get here alpha dot into x1 square. This is less than or equal to 0, because x2 term is missing here, only positive term alpha dot into alpha dot is negative and x1 square is positive. So, it is less than or equal to 0, because x2 is not mentioned here. So, this implies the system is stable, okay, according to the result which we have seen. So, we have seen some theorems and examples related to the Lyapunov stability theory. So, so far we have seen the theorems on the stability using the Lyapunov function for the time varying and time invariant system, and some examples have been seen. So, in the next lecture we will see another type of stability theory. Okay, thank you.